Hi, everyone. Well, now I'd like to talk about the opposite case, the case where we want to use the Schrodinger equation to find energy states for bound particles. All right? And to do this, we're going to develop a simplified version of Schrodinger's equation called the time-independent Schrodinger equation. All right? Here, let's take a look at the notebook and we'll go through this. Okay, so the Schrodinger equation, the time-independent Schrodinger equation is important whenever we have a system where there are energy states, states of well-defined energy. And in fact, that's only possible for a particular condition. And that's that the potential energy, which in general could depend on position and time, that it only depends on position. Okay? So for potentials that don't depend on time, we can say that there must be states of constant energy. Or more formally, that there must be solutions to Schrodinger's equation of the following form. We must be able to write the full wave function, which depends on position and time, as the product of one function that only depends on position, we'll use little psi to denote that, times a second function, phi of t, that only depends on time. Okay? Solutions like this are called separable solutions. Because look, we've separated the time and space parts into separate functions. But we can think of these as standing wave solutions. Because the standing wave solutions, for example, of a wave on a string or sound waves in the sound tubes, they had exactly this property, that they were described by an envelope, okay, that doesn't move, that doesn't change in time, times another function that just oscillates in time. Okay? So think of bound particles as standing waves. All right. Oh, I said if, but I didn't say then. Here we are. If the potential is time independent, then this must be true. Now, if we take this solution and plug it back into Schrodinger's equation, we'll get a really interesting result. I'm just going to tell you the result now because this is the case for our class where the answer is a lot more important than the derivation that leads to it. Okay? We'll talk about the solution now, but then in another video, we'll talk about how it was derived. Anyway, so if one plugs a separable solution back into Schrodinger's equation, then one finds that using separation of variables, Schrodinger's equation splits into two equations. And we find, first, that the equation for the time varying part, phi of t, is given by this, minus I e over h bar times, there we are. So the rate of change of the time varying function, so the rate of change of phi of t is equal to minus I e over h bar times phi of t. Okay? The second equation gives us little psi, minus h bar squared over 2m times second derivative of psi is equal to e minus u of x times psi. There we go. Here, we'll put a box around these. because they're important for us. Actually, the first one's not going to be that important for us, but the second one will be. We're going to use the second one to find bound states or energy states of different potentials going forward in our course. In fact, this equation is so important it has a name. It's called the time independent, Schrodinger equation. All right. And in fact, pretty soon we'll just start saying Schrodinger's equation when we write this down because it's going to be the equation that we focus on. All right. Okay. Um, Here, let's stop this video and then I'll do an example.